Okay, let's see what you got here for number 7, 6.2. So let y equal to the summation as n goes from 0 to infinity, c sub n times x to the n, where they give us where x naught is equal to 0. So y prime for the summation is n goes from 0 to infinity, c sub n times x to the n minus 1. And y double prime is the summation as n goes from 0 to infinity, c sub n times n minus 1 times x to the n minus 2. So we're doing this problem here, so we have y double prime minus xy is equal to the summation as n goes from 0 to infinity, c sub n times n minus 1 times x to the n minus 2. This is minus x times the summation as n goes from 0 to infinity, c sub n times x to the n equal to 0. So the little trick for these problems, we have n and n minus 1. If n is 0, then that term is 0. So we can start it from n goes from 1 to infinity. But if you plug in n equal to 1, then you get 1 minus 1, so you get 0 there. So it's safe here to start this guy at 2. Okay, so just write that here. This is the summation as n goes from 2 to infinity, c sub n times n minus 1 times x to the n minus 2 minus, see, n is traveling from 0 to infinity for this summation, but it's traveling as an exponent for x. So that x is important even for the summation. So we have to write this as the summation as n goes from 0 to infinity of c sub n times x to the n plus 1 is equal to 0. And for this term, we have to have x, this x to a power has to be the same as this x to a power to be able to factor out x to that common term. So here, let k equal to n minus 2. So obviously k plus 2 is equal to n, and k plus 1 is equal to n minus 1. Then over here, we always let k represent that exponent up there, so let k equal to n plus 1. So now we have the summation as k goes from, if n is 2, then 2 minus 2 is equal to k, goes from 0 to infinity, c sub k plus 2 times n is k plus 2, n minus 1 is k plus 1, times x to the k, minus the summation as k goes from here, if n is 0, so k goes from 1 to infinity, c sub, this is n, but k minus 1 is n. So this is c sub k minus 1 times x to the n plus 1, but n plus 1 is k, so this is x to the k equal to 0. Well, I can't factor out x to the k from here and there because both of these summations are starting off at two different indexes. So one starts at 0, the other starts at 1. So we evaluate at k equal to 0, and then we have plus the summation as k goes from 1 to infinity, plus the other summation over here, and k goes from 1 to infinity. So we evaluate the first summation at 0, so that gives us c sub 2. If k is 0, that'll be times 2, and 0 plus 1 is 1, times x to the 0, plus the summation as k goes from 1 to infinity. Go ahead and just do the factoring because we're going to have everything common, right? This is one summation. This is c sub k plus 2 times k plus 2 times k plus 1 minus c sub k minus 1 all times x to the k, and all of this is equal to 0. Now the first part over here, this is 2 times c sub 2 is equal to 0. Everything on the left side must be equal to 0. So 2 c sub 2 is equal to 0. We'll need to know that when we start writing out those solutions for those coefficients. Now, that summation, the term that gives us 0, will be those coefficient and constant factors. So that's simply c sub k plus 2 times k plus 2 times k plus 1 minus c sub k minus 1 equal to 0. If you solve for c sub k plus 2, that's equal to that c sub k minus 1 on the opposite side divided by k plus 2 times k plus 1. So now we can solve for those coefficients. So we start, let k equal to 0. Let's see what we get. We get c sub 2 is equal to, look at this. This is c sub negative 1. We don't know. I don't know what that is, right? So this is k is 2, so this is 0 plus 2 times 1. I don't know what all this is, but I know what this guy is, right? Because this right here says that this is c sub 2. So whatever that c sub negative 1 is, I don't care what that is. I know that c sub 2 is equal to 0, right? From this term right here. Let's go to the next one. If k is 1, we get c sub 3, and this is c sub 0, because this is c sub 1 minus 1, c sub 0, and this is 3 times 2. If k is equal to 2, just take your time. C sub 4, this is c sub 2 minus 1, that's c sub 1, all over 4 times 3. Just find a couple of more. So k is equal to 3. C sub 5 is equal to 3 minus 1. C sub 2, that's all over 5 times 4. K is equal to 4. C sub 6 is equal to C sub 3 all over 6 times 5. Now, so let's see. So C sub 4 depends on C sub 1. C sub 5 depends on C sub 2, but C sub 2 is 0. C sub 6 depends on C sub 3. C sub 3 is right here. C sub 3 is C naught, and this is 6 times 5 times 3 times 2. Now, you'll notice in the back of the book when he writes his answers, he may try to write his solutions fancy. I guess that's a really good word for it. Like you can make this guy fancy right here. You can make this 6 factorial downstairs, but notice if it's 6 factorial, you're missing a 4, right? So you can put a 4 up top and a 4 downstairs, so 4 divided by 4. So you can say 4 times C naught all over 6 factorial. So, or you can just leave the dang on thing just the way it is and just say it's C naught over 6 times 5 times 3 times 2, and just be done with it. Either one is fine with me. But you just notice in the back of the book, he'll have stuff like this, and he'll say this is 4 times C naught all over 6 factorial. So. Now, for this C sub 5, you can make that 5 factorial, but you're missing, what, a 3 and a 2, so you're missing a 6. So you can say that this was 0, so who gives a flip about that, right? So I forgot it's equal to 0, so we don't care about that. Okay, I didn't mean to say who gives a flip. Forgive me for that. That's not a good statement. Bad implication. Anyway, sorry about that. So here, what about C sub 1 over 4 times 3? You can make that, in a sense, 4 factorial by putting a 2 up top and down below. So you can write that if you wanted to, 2 times C sub 1 over 4 factorial. Because that's all you're missing for the 4 factorial downstairs is a 2, right? 4 times 3 times 2. So we put the 2 up top and the 2 downstairs. Make sense of that. So now you want to list out. I write it like this. I just say that y is equal to, always for these problems, C naught plus C1 times x plus C sub 2 times x squared plus C sub 3 times x to the third, and so on. You get the idea? So here, y is equal to C naught plus C sub 1 times x plus, now C sub 2, we get 0. I'm just going to put that there just to hold that spot. We won't need it when we write the final answer. So then, now we're at C sub 3. So C sub 3 was this C naught over 6. So C naught over 6 times x to the third plus C sub 4. This is 2 C sub 1 over 4 factorial times x to the 4th plus C sub 5 goes out plus 4 C naught over 6 factorial times x to the 6th plus, and it keeps on going. So now, notice that I have the combinations of C naughts and C sub 1s, right? C naughts, C sub 1s. We just group them together. We just group the C naughts together. So y is equal to C naught, everything with C naught in it, 1, nothing there, it's just 0, well, whatever that is. But this is C naught here. This is plus x to the third over 6. There's another C naught, that guy right there. So this is plus 4 times x to the 6th over 6 factorial plus, and so on. There's other terms out there that we know not of. And you write it out for a few iterations until you get the pattern, and then you stop. You don't have to keep on going. There are certain courses where we have to actually go out and identify how far do we go to actually get the convergence. Beyond that, you may get 0. So they have like remainder theorems. Courses like approximation theory, would go over that kind of thing. I'm not concerned about that right now. So this is plus. What about the C sub 1? So C sub 1 here times x, C sub 1 with that 2 times x to the 4th all over 4 factorial. And that's all that we wrote there, and that's fine. Okay. So you get the two solutions. And for that particular section, section 6.2, we said that if you know that you're solving a differential equation using the power series about an ordinary point, the theorem says that you're guaranteed at least two linearly independent solutions. Well, one solution would be that 1 plus x over x to the third divided by 6 plus 4x to the 6 over 6 factorial plus and so on. The second solution is the x plus 2x to the 4th over 4 factorial plus and so on. And it's supposed to look like that because that's the pattern for the superposition principle. What are we saying when I say that? I'm saying that here that y sub c looks like c sub 1 times y sub 1 plus c sub 2 times y sub 2. Okay. Any questions? All righty. Well, I didn't go over anything new today. I will cover 6.3 on Wednesday. That's the only section that we have. After that, we'll take the test. So the test will consist of 6.1, 6.2, and 6.3. So I will cover 6.3 on Wednesday. Review on Monday and give an introduction to Laplace transforms. Take the test on Wednesday. The test on Wednesday of next week would only encompass 6.1, 6.2, and 6.3. Okay? Thank you.